Circuits with multiple capacitors can be redrawn as if there were only a single capacitor and a battery, just like we've already done with circuits with resistors. By reducing the circuit this way, the circuit becomes easier to study. We call this process finding the equivalent capacitance for capacitors in series, which is C sub S, and parallel, C sub P. We'll start with the circuit with just two capacitors. Let's use our prior knowledge and what is the voltage across each capacitor and what is the charge on each capacitor. The voltage across each capacitor is the same because they're in parallel. So we can say that V1 is equal to V2, and once you have two quantities with subscripts equal to each other, you can just replace it with the V. The total charge will be the sum of the charge on both capacitors here. So that would be Q is equal to Q1 plus Q2. And again, we're just going to use the charge on one plate here because we know that each capacitor is neutral, but we'll take the charge here plus the charge here. We'll use what we found on the previous slide where the voltages are the same and where the total charge is the charge on each capacitor, and then we'll use our definition of capacitance, which was C is equal to Q over V. So we start right here, this equation here, we replace each Q with CV. So we have CV is C1V1 plus C2V2. But what do we know about V1 and V2? They're equal to V. So we now have CV equals C1V plus C2V. Everybody has a V, cancel it out, and we find the equivalent capacitance for capacitors in parallel is you just add each individual capacitance. And if you have more than two, it's the sum of all the individual capacitances. The sum of the voltage drops across each of the capacitors in a series circuit equals the voltage of the battery. It's kind of like Kirchhoff's law, as a matter of fact. You start with a V here, and then you transfer some energy into the capacitor here, some energy here, and when you're all done, you come back with zero on this side, zero potential. So V is going to equal V1 plus V2. When you're in equilibrium, after these are fully charged, let's see, this will have a minus Q charge here. This will have a plus Q on this side. Since no charges are flowing, you have to have the same amount of charge here as here. So this also will be negative Q. If this were anything else, you would have charges flowing between the two of them. They have to be equal because this wire is neutral. There's no more current flowing. That would put a Q over here. That means the charge on each capacitor is the same. So we can replace Q1 and Q2 with just Q. We now have three equations to work with. The sum of the voltage drops across the capacitors is equal to V. Each charge on each capacitor is the same. And then here's your definition of capacitance, again in a slightly different format. So we will start with this equation here and substitute in for V, Q over C. So we have Q over C is Q1 over C1 plus Q2 over C2. We know that all the Q's are the same. So we can now have Q over C equals Q over C1 plus Q over C2. We can cancel the Q's because they're all the same Q. And we're left with 1 over C is equal to 1 over C1 plus 1 over C2. And if you have more than two capacitors, this is the more general equation. Relating this to resistors, we find that the equivalent capacitance is like finding the equivalent resistance, but it's reversed. Capacitors in series are added like resistors in parallel. And again, the caution, when you solve for capacitors in series, when you do the math on the right side, that doesn't give you the answer for the equivalent capacitance. What do you have to do? You have to flip that. You're finding 1 over C sub S. You want C sub S. So do the work over here and then flip the answer so you can get the capacitance in series. In parallel, Capacitors in parallel are added like resistors in series.